So today, I want to give you a little example, which has traditionally been considered tricky in separation logic. Well, not just this example, but a whole class actually, but we'll cover it through one example. And it's about writing programs that manipulate graph structures. Okay. So when separation logic was invented, it was thought that it's best suited to manipulate data structures which you can split into disjoint pieces, right? That's why you have the star operator in separation logic. So things like linked list are a good example because every linked list you can split into two. Or a tree, right? Linked tree, single linked tree, you can split it into two, and you can have a recursive sub-procedure go and work on the left child, recursive sub-procedure go and work on the right child. But with graphs you cannot do that. So graphs have traditionally been a little bit difficult. I mean, people have verified them, but it was always very tricky. So now I want to show you that now with this auxiliary state that I have been talking about for the past 3 days, you can actually do it quite nicely and easily. Okay. So let's make things concrete by writing an example program that you want to verify. So what the program does, it takes a graph, and then it traverses the graph from some node that we pass, initial node that we pass as an argument, and it starts pruning edges, and the idea is to get a spanning tree in the end, okay? And we do it concurrently just for the fun of it, okay? So this is the procedure, span, okay? It takes the initial pointer from which we want to proceed, returns a Boolean, which we will use to indicate whether we succeeded or failed, and we'll see what success is in this case and what failure is. If x is a null pointer, well, I guess that's the failure, right? Okay, otherwise, we do a cas. And I'll explain the data structure and all the notation later on, but let's write the program first. Okay, let me write the program and then we'll discuss it. Okay, so the graph is represented in memory using a link structure like this. Okay, every node, in every node you have some value, and then a pointer. This is a binary graph, okay, binary directed graph, which means every node has 2 children. So it looks something like this, okay? And then we can have things pointing back or forward like this, or stuff like that. Oh, there is more. There is one more field, actually. Let me not call this value. Okay. So the fields are m, and then L for the left child, and R for the right child. Okay. M is a Boolean bit, which says whether the node is marked or not. And these are and then we have, I will address them as x.m for every node x. Okay, x.m, x.l, and x.r. Of course, you can address them as x and x plus 1 and x plus 2, but I don't bother with that now. This is more readable. So what's going on with the algorithm? Okay, if we get a null pointer, well, there's nothing to mark, but we return false, all right? Because, well, people should not be sending us a null pointer to start with. Then we try to mark the node x by switching its mark bit from false to true. We may fail or we may succeed. We will fail if somebody else already beat us to the punch and marked the node before us. Okay, in which case we just say, well, we didn't manage to mark, so we exit. But if we do manage to mark, okay, if B is true, then we fork two recursive subprocedures to cover the left and the right part of the graph. Okay, and when we come back, then we start pruning the edges. If we got a success outcome out of the left call, okay, I'm sorry, if we got the failure outcome of the left call, then we prune the left edge. If we get the failure outcome out of the right call, we prune the right edge. But in either case, we return true. So just to see how this works on an example, to convince yourself intuitively that this does compute a spanning tree, here's a little graph. Okay? And then we'll run this procedure on it. Okay. Now let me call them A, B, C, D, and E. So let me see if I can animate now this. So we start from A, and we mark A. Okay. Then we fork two subchildren, B and C. Okay. All right. So their respective threads manage to mark them as well. Okay. So now the threaded B marks two children. The threaded C marks two children as well, one for looping and another for going to E. So now the C1 sees that, well, the node C is marked, so this edge now has to be removed. So let me put an X on it. It has to be pruned. But it manages to mark the E node. Now the B right child sees that, oh, okay, E is marked, so I have to return false here in order to prune this edge, but it manages to mark D. And now the recursion is coming back, and the edges that have been marked for erasure, for Xing, get removed, get pruned. Okay. And you can see we get a tree, and it's the spanning tree of the graph. So there are two things that obviously that we want to prove about this algorithm. First, that what it produces in the end by pruning is a tree, and moreover that, well, that it marks all the nodes. So it is a spanning tree of the initial graph. Okay. Can we intuitively convince ourselves that this produces a tree? So the first step. Well, let's see. Okay. Okay. If we get X is null, then trivially we got an empty tree. So that's not so interesting. But if we manage to mark, what happens here? Let's see. Let's assume that this produces a tree, and then we can see that if the recursive calls produce a tree, then the whole thing will produce a tree. Why? So, okay, let's imagine that we got true and true here. So then the call to span x.l and the calls to span x.r produced trees, or marked some edges, okay, and pruned some, marked some nodes and marked some nodes and pruned some edges. And we will insist and we will show that the stuff that they ended up marking are disjoint sets of edges. Okay. So we got two disjoint sets of edges. RL and RR are true. We are returning true, but what is the with the node X now being marked. So if we got some subtree on the left and subtree on the right from the calls to XL and to XR, and now we are just putting a node B here. Okay, we are getting a tree under the condition that actually there are no edges going back and forth between these two. So we will need to record somehow in our specification then that the outcomes of some information that will let us conclude that the outcomes of span XL and span XR, even though they produce these joint sets of nodes, are such that we didn't get edges back and forth between those two. And similar situations arise if you get one of these guys to be false. Okay, why does it mark all the nodes? Why is the tree that is going to be produced a spanning one? Okay. Well, we will need to consider the situation. We'll need to introduce a concept of a front of a graph. Okay, a front of a graph is a set of nodes that you can reach from okay, front of a tree, or front of a set of nodes. In a graph G, front of a set of nodes T is the set of nodes T prime, such that I have an edge from is a set of nodes X, such that there exists X prime, edge X is in G. Okay, so the front of a set of nodes T in a graph G is a set of nodes that are reachable from anything in T in one step. Okay. What we want to prove here is that by the time the spanning procedure finishes, the set of nodes T that it will mark will be such that its front is all marked. Okay? So we marked some tree, but the point is, if we proceed to follow the edges out of the nodes of that tree, we will not be able to find anything else which is unmarked. That's why we terminated. If there was something to be found, we would have proceeded to keep marking. Okay? So if we get a tree whose front is marked, okay, then it means we have, if the graph G is actually connected, that means that T contains all the nodes of the graph. Okay? So those are the concepts that we will play with when writing the specification for the span procedure. Okay. So now how do we want to specify and verify this thing? And in particular, okay. So typically, or in the past, when you would want to work with graph algorithms, people are always trying to split the graph somehow so that the recursive calls work on one part of the graph, the left recursive call works on one part of the graph, the right recursive call works on another part of the graph. But as you can see here, if we do that here, what will happen, as we are following the edges, as the left guy is following the edges of the left subgraph and the right guy is following the edges of the right subgraph, they will eventually start encroaching onto each other's territory, right? Because, well, we had edges like this, right? So the left guy follows and then they clash. So we will not be splitting the graph in two. We will keep it as a whole. But there will be something else. There is something else that wants to be split in two when we are forking parallel threads. And that something will be an auxiliary state that we will add. Okay, and in particular, what should that auxiliary state be saying? Okay, from the description that I gave you, I hope it is in some sense intuitive that when a thread marks its node, in some sense it gets an ownership of the tree, or I'm sorry, of the subgraph that is reachable from that node. Because if that thread marks the node, okay, then anybody else who comes in and sees that node marked, they immediately terminate, right? They will try to cast on that node, they will get a false, they will immediately finish. Okay? So the important concept here is, if I'm a thread, I want to know what are the nodes that I have marked versus what are the nodes that other people have marked. So that's the auxiliary state that we will add to this example. So a piece of information saying what is it that we've marked and what is it that everybody else has marked. And that's the stuff that we will be splitting across calls to recursive calls in parallel composition. Okay, so we will keep AS and AO variables as we had. Yes? Okay. This will be just a set of nodes which are marked, so that's a set of pointers for us, right? Finite set of pointers. In fact, just to make it clear that this is about marked nodes, instead of AS and AO, let me call them mu S and mu O, for mu for marked. In the join state, so AJ we will have a heap which is storing our graph and a ghost variable, or auxiliary variable, which will be the mathematical representation of the graph. So what is this thing? Okay, and the projections, by the way, I will call them sigma j for heap and gamma for the graph. And gamma is of type graph, and that is, let me write it out, pointer arrow bool, cross pointer arrow pointer, cross pointer arrow pointer. Basically reading for each pointer in the graph, it's reading the fields M, L, and R. Okay? And I will write this projection as a nodes of gamma. I'm sorry, so this says if a pointer I pass, if it's true, then that pointer is a node in gamma. If it's false, then the pointer is not a node in gamma. And this is for left children. Yeah, left of gamma. And right of gamma. Does this make sense so far? Yeah? Okay. So let's write a specification for span. We will need two variables, M and G, two logical variables. And we say something like this. The current graph gamma is a subgraph, and I'll define this relation of G. And the set of nodes that I start with having considered marked by myself are M. And I need to know that X is either a null pointer or something in the nodes of G. Okay, I don't want to work really if somebody passes me a random pointer which is not in my graph. Okay, so that's the precondition. And the postcondition, okay, we have a Boolean result. And then the postcondition says the new graph, which I also call gamma, but now it's in the postcondition, is still in this subgraph relation with G. And there exists a set of nodes T, which is the new stuff that I've marked. Okay? So I will terminate with some set of marked nodes T, which I'm adding to what has already been marked by my caller, by the thread that invoked span. And if the return result is true, then okay, there is some relation here which I will also define eventually that I call here subspan gamma G mu xt okay, else T is empty and X is in null union mu, where by mu I denote the sum of mu s and mu o. So what is this saying? Well, okay, I'll have to define these predicates. So let's do that next. Okay, I say that graph G1 is subgraph of G2, subject to a set of marked nodes M, if the following holds. They have the same set of nodes. Okay, I'm not removing any nodes, I'm just removing edges. And for every unmarked node, the children in the graph G1 of X are the same as the children of the graph G2 of X. So unmarked nodes, nobody removes edges out of unmarked nodes. If you want to remove an edge, you first have to mark the node. Okay? And for every x in the set of marked nodes, left children in G1 of x are, well, in this set, null, and left G2 of x, and in the same dual for the right. Okay, this says that, okay, this already explained. Nobody removes edges out of unmarked nodes, but if a node is marked, then we cannot arbitrarily go from G2 and change the edge randomly. All that we can do is either keep the edge the same or remove it by writing null into it. Okay? So G1 is a subgraph of G2 if basically they have if G1 has a subset of the edges of G2. Okay? And that subset is a full set in the case of unmarked nodes. Okay. So what does this say is if M is empty, what does this say for the two graphs? They are exactly the same graphs. So you can see, if we call the procedure span, the top call for the procedure span, so not one of these recursive ones, but the top call, will start with all the nodes unmarked. In that case, I'm just saying this G is going to stand for my initial graph. Okay? And gamma changes, but I know G is the name for the initial graph, and I can then compare all the results to it in the postcondition. So that's that. Now we need to define subspan. Okay, subspan G1, G2, M, so 3 parameters, and then X and T. Okay, that says, that's defined to say that T is a tree, or I should call it subtree, in the graph G1, rooted at X. So T is a set of nodes, but if I look at that set of nodes in the graph G1, the edges of the graph G1, then T is a tree. Okay? I won't define subtree, but it's easy to define it. You basically say, well, there's no cycles between the nodes in T, from T. And we want front of T in G1 is a subset of T. So T is all marked, and if I try to leave it, there's nowhere to go. I have to stay in the tree. There's no edges out of that tree, except outside of the tree, yes. And if I look at that set of nodes in the in the graph G2, okay, then that's subset of M. So all the nodes are marked. Okay, so you see here, gamma 1, gamma 2, and M are instantiated with gamma, G, and mu. So what I'm trying to say here is that we're going to get a tree, set of nodes T, which is a tree in the ending graph. Okay. There's no nodes, there's no edges out of that tree in the ending graph. So that's the second condition. And the third condition says, if I look at the set of nodes in the initial graph and consider the edges, well, all edges lead to marked nodes, which is why I terminated, because I had, well, basically nothing else to mark by following the edges out of those nodes. Okay. So why is this the right spec? Okay, why is this a good spec? First of all, it's well, it's strong enough. It will be strong enough for us to pull off the recursive calls. Okay, I will use this spec for the whole procedure as well as for the recursive calls. But also, it's the right thing because it says, for the top call, what do I know about the top call? Since it's a top call, it means nobody's interfering with it. Okay, that means that mu of O for that top call will be the empty set. Right? Nobody has marked any nodes by the time I make my top call. We will also, for the top call, instantiate M with empty. So mu S will also be empty. So we are saying nobody has marked anything, us or anybody else. In that case, gamma will be the full, G will be the initial graph, as we already discussed, right? Because no nodes are marked. And here we'll get that in the case of a success, we got a subspan of the initial graph, which means we got a subtree of the initial graph with the front marked. Okay, and as I said initially, if the front of a tree is marked, that means if you follow the edges out of that tree, starting from the root, for example, you keep staying marked. Okay? And if your initial graph is connected, that means you have, if every node is reachable, every node in that graph is reachable from the top node, but every node must be marked, right? Because we got a tree, T, and we cannot leave it. Does that make sense? So if you work it out of those definitions, if you start with mu S is empty and mu O is empty, you will and G is connected, you will get that you will get that the T must contain all the nodes. Okay, so now we need to write a resource invariant and the transitions for this program and then verify it. Okay, where are we? Okay, so our resource invariant says, remember, it's a predicate over sigma j, mu s, mu o, and gamma. So it says we have a graph laid out in the sigma j, in the heap sigma j. I'll define graph eventually. Domain of that graph, so the nodes of that graph, is precisely the nodes of the mathematical representation that I use for that graph. Okay, and for every x, b, xl, and xr, if physically the node x points to b, xl, xr in the heap, then I know that, well, this, in the mathematical representation, these are the children. So children of gamma, children of x in the mathematical representation gamma are exactly xl and xr. And this b is true if and only if the node is marked. So okay, and then I have a graph predicate which says some piece of heap stores a graph if what? Well, first of all, it's a valid heap, so it's not one of those undefined things. So valid sigma j, and for every x in the domain of sigma j, there exists a b, a Boolean, and xl and xr pointers, such that x points to b, xl, xr is in the heap, and xl and xlr are either the null pointer or nodes in the graph. Is this clear? So something is a graph if all the pointers in it are pointers to triples. M, XL, XR, where XL and XR are another pointers to the triples. Okay? That's for that part. And then this part says that the graph in the heap and its representation gamma actually are the same thing. So that I can just use the mathematics. I can use gamma when I need to talk about its components rather than looking into the store. Okay, what are the transitions? I guess I can write them here. Well, we first have a transition for marking, which corresponded to the cast in the original program, and the transitions for pruning the edges. Okay, so the mark transition. Okay, we pass it a node X, which we want to mark. And I'm using my hand wavy notation from yesterday. If I start with some mu s being m, and the heap sigma j being x points to false, xl, xr, union something, I'm just going to write the Boolean true here and add x to the set of marked nodes. And nothing else. Okay, so that's a transition for marking a node. Then we need a transition for pruning the left edge. Prune left trans. It prunes the left edge of XL. So that's defined to say, well, you must have marked the node X. If you want to prune edges out of X, you better own X. Okay? So you have X in your mu S, but maybe you have some extra stuff as well, which we call M. Okay, then the contents of the node X in the heap is true XL XR, and then maybe you have some other stuff in the heap, and the representation gamma is some graph G. Then what's going to happen? You keep the same set in your marked nodes, but you just replace this XL with a null pointer. Okay, and you need to change the mathematical representation correspondingly, right? So now this keeps the same set of nodes. Remember, this gamma was a triple of functions. So we keep the same set of nodes of G. The set of lefts becomes, I don't know how to write it, but maybe I take what the left children of G that I had and change that to say that a point X now we return null. And the set of right children is the same as it was. Okay. And then the prune right transition is the same, except you pass XL along, but you nullify XR. Okay. So now we need to write the version of the algorithm with annotated primitive commands. So let me write the algorithm first, and then I'll define this annotated primitive command second. So it's almost the same as before. Okay, if X is null, then ret false. else, now we don't say cas anymore, we say try mark. Okay, because this will now change X as well as auxiliary state. Okay, if B, then XL is going to be read left, XR is going to be read right, and I'll define this. Okay. Then we prune left. And similar for the right. And return true. Else, that false. Okay, so try mark used to be cas, but now we just say it's a relation between return result, input state, and output state. So I'll write it like return result, and then I don't have to write the states, which says if I'm returning true, then I took a marked transition on the input states, else idle transition. But then I know, idle transition, let's put it like this. Prune left says, well, I'm just taking the prune left transition. And I don't care about the return result because its type is unit. Similarly for prune right. For read left, okay, we are taking the idle transition, so lambda r, idle. But we know that what we are returning is the left child in gamma of x. So remember, this idle with P was this set of xx such that x is in I and P of x. And similarly for read right. Okay. So the next step, after we have defined transitions and actions, we need to give stable specs to each primitive. So we need stable specifications for try mark, read left, read right, and prune. So let's start doing that. So for try mark, it turns out that the spec looks like this, stable one. We start with some gamma, which is a subset of our initial G, and mu s is m, and x is in nodes of G. And what we get in the end is, let me write it out and then we'll discuss it. Okay. So we start with some graph, with some set of marked nodes, and we know that we are calling try mark on something which is a node. We remain here. This gamma may differ from the initial gamma, but it's still a subgraph of G. If we succeeded, then what's happening? we have managed to push X to mark X, okay? And by marking it, we know that the edges out of it are not changed in the new graph. Does that make sense? Okay. Otherwise, if we failed, well, we didn't add anything to the set of marked nodes, but we know that X is marked, just not by us, right? It's marked by somebody else. And then we don't know anything about the edges out of it anymore, because that guy who marked it may have changed them. Okay. Why is this stable, by the way? Let's see. Why is this property stable? Can anybody guess? I mean, I think we discussed it already, but maybe you can repeat it. I have some graph gamma, which is subset of G. I'm sorry, here I have to say mu everywhere. The intervening threads can mess with gamma, but they cannot mess with G. G is a constant. Okay? But how can they mess with gamma? They can only remove edges out of the nodes that are marked by them. Okay? So in order to mess with it, they first have to mark some node and then remove the edge. Okay? Now, if they mark a node and remove the edge, well, that thing still says that new graph will still be a subset of the original G, because that's how I defined this subgraph relation. Okay? So in particular here, in the success case, we know that X is marked. We marked it. So the set of marked nodes here is one larger, at least one larger than the one that we had here. Here, in the precondition where X was not marked, we knew out of this relation that the children out of X, of gamma and G, agree. Here, X is marked, so this relation doesn't tell us that the children of X and of X at G and gamma agree, which is why we postulated separately as a separate property, a separate conjunct. Okay? So this relation sort of decreases in its expressiveness as we go, but it keeps being true. Okay. Okay, let's write the spec for prune. That's going to be easy. We start with some graph G, gamma. We know that X is in a set of marked nodes for us. And we know that the children of the graph at X are some XL and XR. In the end, we are going to get, can anybody tell me? Just to wake you up, I'm sorry. Okay, this just keeps propagating. This keeps propagating. And what am I going to have here? XR. Yes, I'm sorry, it is R, yeah. Okay. So let me not write the prune right, because that's the same, except you swap the x's and nulls. And let me just write quickly the read left specification. This thing with gamma being a subgraph just keeps propagating again. Am I going to have need more space? And what else do I need to add here? I'm reading the left child of x. So I need to say something about the return result. R equals XL, yes. Okay. What would happen if I removed x from here? If I tried to read a left child of a node which I didn't mark, would this spec hold? I'm sorry? Somebody said something. No. No, it doesn't hold, actually. It doesn't hold at all, because if you try to read from a left child or a right child of a node that you haven't marked, somebody can go and mark that node and then prune the child. So this R doesn't necessarily have to be XL. It can become null underneath you without you knowing. So this specification will not be stable. That specification would not be stable. That's why I insist that I only read children of nodes that I have marked, because then I actually know that the result will make sense. Okay? That's why we were reading the node here inside the if block, only after we have actually managed to mark the node. Okay, so now we can write the proof outline. We're about done. Okay, so the precondition that we wanted for span is, okay, gamma smaller than mu g, and mu s is some m, and x is in null union nodes of G. Okay. The first line was testing for null. Okay. Well, then, in that case, we have the same thing from the line above, plus we know that the result is false. Well, and moreover, that x is null. Okay, so x certainly must belong to null, union marked nodes, and R is false. So we have satisfied this part of the postcondition, right? There certainly exists a t that we want, and that t is empty, such that empty is equal empty, and x is in null union marked. Well, it is in null union marked because it is null, right? Else, okay, well, now we know everything that we knew before, except now x is not null, so we just write x is in nodes of G. So now we do the try mark. And is it on the on the board? So you see the precondition matches what we have. Okay. And the postcondition, I have it here, so let me just write it down. Okay. Somebody correct me if it doesn't match what's there. that was supposed to be.
So I think that implies that X is in the mark set. Mu S equals M, X is.
I made a mistake here. It should have been mu. Right? Right, because here I actually know that it's not in my marked set, it's in the others.
That was blind.
Yes, yes, I'm sorry. Okay, the next step is if B, then, well, let me not copy everything, but we are in the then part. XL is read left of X. And now I have erased the spec for read left because I had to. But trust me, it's exactly this. It's exactly what you this plus the then part of this stuff. Okay. So we can write the postcondition. Gamma smaller than G, and mu S is X union M. And children of gamma X is equal to children of GX. And XL is the left child. Okay. When we do the read-write, similar thing, except this conjunct propagates by framing. This conjunct will not be in the precondition of read-write because it's a new piece of information, but we know how to propagate those things that we want to propagate, right? Just by framing. So let me not write that out. What we get here is mu S is X union M, and XL, XR is children gamma X is equal children G of X. Okay. So if you come to this point, basically the original graph didn't change. The edges of the original graph at X were not changed. And now they are XL and XR. So now we are getting ready for the recursive call. That's the tricky part. All right, so we have this thing, and we need to split it into the form P circle star Q. In fact, we'll split it into P circle star Q circle star R, where R will be a frame. So the P stuff will go to the left thread, Q stuff will go to the right thread, and the R stuff will just propagate. So here's what I have for the P stuff. Okay. Gamma smaller mu G, and mu S is empty, and XL is in null union nodes of G. Here we have gamma smaller mu G, and mu S is M, and XR is in null union nodes of G. And we have a third thing here, which says mu S is X, and XL, XR is equal to the children of this. So this is a predicate over shared variables, over stuff in the shared state. So it holds on all, well, wherever. By splitting using circle star, you don't change its validity. It holds on both sides. What matters, XL is in now union nodes G. That's just trivial. That's not listed here, but it follows from here. Why? Well, we know that X is a node in the graph, so it must be among the nodes of G. Well, and then adding null doesn't change anything about the truth of this property. What else? So the only important part is this S variables. Okay, here we had that the set of marked nodes is X union M. I have to split that among my children. So I'm passing empty to the left child, I'm passing M to the right child, and I'm passing X just like that to the frame. So now these two preconditions match exactly the precondition for span. So I'm ready for the recursive call. So I just copy here the stuff from there. Oh, by the way, mu is the sum of mu S union mu O, right? Now S's and O's change between these threads, but O's also change to adapt from the fact that, point being mu is equal across these threads, right? Mu S plus mu O is invariant and it's equal in each thread. So that's why I just keep writing this mu without actually much regard for the fact that I'm modifying mu S and mu O. Doesn't matter. Okay, so here now we have some tree TL such that mu S is empty plus TL, so just TL. And if RL, then subspan gamma G mu XL TL, else TL is empty and XL is in null union mu. That's for the left guy. For the right guy, the same thing, except we have TR and RR. So let me not write that out. And instead of mu S is equal TL, we say mu S is M plus TL. And this stuff is the frame, so it propagates. So I can write, how do I do that? Let me just write out once I conjoin all those three things, what do I get? Okay. And what I get is gamma is smaller than G. And out of there, I get XL, XR are children of gamma, of X at gamma, but also children of X at G. Okay, and I know that exist trees TL and TR coming from the left subtree and the right call respectively, such that my mu S is X taken from here, union TL taken from here, union M union TR taken from here. Okay, makes sense? And if RL, then subspan XL TL, else TL is empty, and XL is in null union mu. And here if RR, the same thing exactly, which we would get from the postconditions of these two recursive calls. Okay. So now we are pruning. I guess I should just speed things up because this is, you should have to trust me. I did all of this in Coq, so it holds. Well, okay. All right. I'm running out of pens. Let's use a green one. Okay. Okay, what do we have here? We had prune left. And if not RR, then prune right. And now you can copy this over there, but changing some stuff. So let me do it in place instead of copying. What changes? Actually, all of it holds, and then, if I'm correct, then we are just adding that channel gamma at X is if RL, then a pair, then XL else null, and if not R, if RR, then XR else null. So it becomes an additional conjunct. And so now, okay. Now I need to consider 4 possibilities. This guy is true and false, or false, and then this guy true or false. But one does get this. Exists a tree T, and that will be equal to X union TL union TR, such that mu S is M plus T, and you get a subspan of XT, which was the then part here that I erased. Okay. So that's exactly what we wanted if we are returning a true. So after here we get return true. So that's it. Now obviously the tricky part is to go from here to proving subspan for the whole big tree. Okay, and one does need to go through 4 cases. And the only interesting case is when you got true here and true here. Okay, so then you got subtrees TL being something like this here, and TR being something like that here, and you're trying to add the node X as to produce a whole T. So this will be our T. So the subspan had 3 conjunctions. One was to prove that you get a subtree. So we got a subtree here and we got a subtree here, but we needed to know that there are no edges between them in order for this whole thing to be a tree. And we know that there are no edges because we know that the front of TL is included in TL. Right? If there is an edge going from TL to TR, that means that there must be one node in the front of TL which is in TR and therefore not in TL because they are disjoint. So we know that there are no edges. Then we need to prove that the front of this whole thing is included in itself. Well, that's easy because the front of X includes the nodes TL and TR. And the front of TL is included in itself. Front of TR is included in itself. The whole thing then therefore has a included front. And then we also need to show that this whole thing is marked. Well, we know this was marked. We know this was marked. We just marked X because it's in mu S. So the whole thing is marked as well. And we got the proof of span. Okay, so that's it for me for today. Any questions? Yes?
You said you formalized it in Coq.
Yeah.
That Coq
It is on the web actually. I mean, we published this in a paper at last year PLDI, so just look at that paper and the associated code files. Yes?
There's sort of asymmetry in how you divide up each S in the parallel subcalls.
Yes.
You sort of arbitrarily put
Completely arbitrarily, yes. It doesn't matter, that's the point, right? Okay. Because whatever you pass in here as an input, stuff is going only to be added.
Could you just put in could you put M in the frame instead?
Yes. In fact, yeah, that would be, well, fine. The reason why I didn't put M to be empty in the initial, in the spec that I gave you was because I knew that I will call the span at some point with M not being empty, and then I would have to explicitly add the frame. But yes, you can, the best spec is the one in which M is empty, and then you just say, I got a tree in the end, and it's, my mu S is that tree rather than M plus that tree. Yeah. Any other questions? Okay, thanks guys.
So on behalf
Oh, gee,
of
okay.
all of us here, I would like to thank you and
Thanks.
present you with this certificate. I think that
Okay.
it was very nice of you to take ownership of these 4 lectures and for pointing us to the state-of-the-art in concurrent program
Okay.
verification.
Thanks guys, hope you enjoyed it. Okay.